Okay, so in our last two sections, we try to describe our qualitative data and quantitative data using a graphical method. Okay, so in section 2.1, we talk about bar graph, we talk about pie chart, we talk about frequency table. Okay, to describe our qualitative data set. Okay, in section 2.2, we had a dot plot, we had a histogram, and we had a stem and leaf. We use these three diagrams to describe our quantitative data set. Okay, now so let me add few more for the histogram. Okay, now so depending on the size of data set, we can pick the number of class interval. Okay, so whenever we are constructing a histogram, we need to have a table. That table must contain a class interval and a frequency. Okay, so here, so before you draw histogram, you need to have a class interval. Okay, and the class interval, the width of class interval has to be same. Okay, every class interval must have the same width. Okay, then next we need frequency. Now instead of frequency, you can also use relative frequency. Okay, so it's not that you have to use frequency, you can use relative frequency. Now how do we calculate or how do we find the relative frequency? Does anyone recall? So for example, just let me take an example. For example, we have class interval 0 to 5, 5 to 10, 10 to 15, 15 to 20, 20 to 25. So this is the class interval. I have the frequency for 0 to 5, 1, that is 5, 8, 9, 15. For example, this is given to us. Okay. Now, so if we have this frequency table, what does it mean by the frequency is 8 for this interval 10 to 15? What do we understand? So we have the class interval 10 to 15 and the corresponding frequency is 8. What does it mean for us? What do we understand? What is that 8?
Between 10 and 15, there is 8 people.
Yes, 8 measurement, right? So yes, between 10 and 15, we have 8 different measurement. Okay, in the similar way, we have 15 measurement in between 20 and 25. Now, how do we calculate this relative frequency?
We divide that by the total amount of measurements.
So to calculate the relative frequency, we divide each frequency by the total measurement. Okay, and to find the total, we add all this frequency. So 15 plus 9, that is 24 plus 8. 24 plus 8, 32 plus 5, 37, 38. Just correct me if I'm wrong. Now, just in order to find the relative frequency, you divide 1 by 38. Okay. To find the relative frequency for 5, you divide 5 by 38. 8 divided by 38. 9 divide 38. 15 divide 38. Can anyone help me? What is 1 divided by 38? If you have two digit after decimal should be fine. 0.03. Okay. 5 divided by 38. 0.13. Okay. 0.2 or 1. 2, 1. Okay, 2, 1. 9 divided by 38 is 0.24. Okay. 15 divided by 38, 0.4. Okay. So this is the relative frequency. Okay. And you can use this relative frequency. Okay. This can be height for a bar in a histogram. Okay. It's not that you have to use the frequency. You can use the relative frequency, and this relative frequency is the height of a bar in the histogram. Okay. Now, the next, so for example, if we have a data set less than 25, okay, Okay, so number of observation. So for example, if we have a measurement less than 25, okay, if your data set has a measurement less than 25, I would recommend you to have at least 5 to 6 class, okay. So number of class interval, okay. So at least 5 to 6. If you have a measurement less than 25, try to make the 5 to 6 class interval, okay. If it is in between 25 and 50, so if your measurement is, the number of measurement is in between 25 and 50, at least, so you can have a class interval from 7 to 14, okay. So make sure to have at least 7 class interval. You can pick any number between 7 to 14, okay. And if the number of observation is greater than 50, okay, greater than 50, then I would recommend your class interval, the number of class interval, to be any number between 15 and 20, okay. Keep this in mind. So depending on the size of the data set, we can pick the number of class interval. And on your exam, it will be always like less than 25, okay. I will not give you the data set with more than 25 measurements. So make sure to have at least 5 or 6 class interval, okay. Now let me draw a histogram here, like this. So we have this histogram. For example, this is the histogram for any data set, okay. So this is the histogram for any data set, okay. Now if we decrease the width of the class interval, okay, if we decrease the size of a class interval, okay, to a very small, or if we decrease this width of each class interval to be small, the histogram looks like, okay. Now let me draw the histogram, okay, and the width of the class interval is small, okay. So this is the histogram with a small width, okay. Now let me have more small width, okay. Now our histogram, for example, let me pick the very small, the width of the class interval to be very small. Okay, now if we keep decreasing the width of the class interval, our histogram, it looks like a curve, okay. Now if you try to construct a histogram with a smaller width than this one, then our histogram, it looks like a curve, okay. So for example, let me try to draw it very small. So our histogram, it looks like, it appears to be like a smooth curve, okay. Whenever we choose our class interval to be very small, our histogram appears to be a curve, okay. Now from from section 2.3 onwards, we will use a smooth curve to represent the histogram, okay. So whenever you see a smooth curve, you have to understand that is a histogram with a class interval with a very small width class interval, okay. So we will be using the curve, smooth curve, to represent our histogram from section 2.3 onwards. Okay, so this is about what we did in our last class. Do you have any question before we start 2.3? Okay, now, so here you see the smooth curve. So this is a histogram. Okay, this is a histogram. It has a vertical bar. Okay, it has a class interval, and the size of the class interval is very small. Okay, now in this section, okay, so we will be using numerical method to describe our data set. So in 2.2 we use graphical method. We had a dot plot, we had a histogram, we had a stem and leaf. Those are the graphical methods of describing our quantitative data set. Now in this section we will use the number. Okay, we will use numerical method to describe our quantitative data set. Okay, so here, so the numbers, for example, we will try to find the mean, we will try to find the median, mode. So mean, median, mode, these are the some of the numerical method to describe our data set. Okay, there are like the standard deviation, there is the range, okay, there is a variation. These are also the numerical method to describe our quantitative data set. Okay, and in this section we will focus on finding the nature of data set. Okay, we will try to find a number. Okay, we will try to find a number that cluster to a center. Okay, that cluster to a center of the data, or we will try to find the central tendency. So finding central tendency means we are measuring. Okay, we want to know whether the data cluster or center to some numerical value or not. So in this section we'll be finding mean, median, and mode. Okay, so whenever we use this numerical method, we are trying to study two different characteristics. Okay, so the very first characteristics is, so we try to understand the central of tendency. Okay, so we want to know central tendency. It means, so this is the tendency that the data is cluster or center about some numerical values. And the next characteristics we can find with the help of this numerical method is variability. So like how the measurements are spread. So we want to know the spread of measurement. Okay, that is the variability. And okay, so if we are looking the spread of data measurement, that is the variability. Okay, and if we want to find a number at the center of the data set, that is the central tendency. Okay, so these are the two characteristics that we can get with the help of numerical method. And in this section we will focus ourselves on finding the central tendency. Okay, we will find a number, okay, which is at the center of the data set. Okay, so if we are looking at a number at the center, that is the central tendency. Okay, spread means how far our measurements are from each other, that is our variability. Okay, now for example, let me go back to our this data set here. So we have these 100 measurements. Okay, so do you think this data set has more variable? How the measurements are spread? How far they are from each other? Is it too far from each other? Like if we look at the smallest measurement, the smallest measurement is 32.7. Oh, not, I think it's 30 point something, right? So, or is it 32.7? The smallest measurement, it should be 30 somewhere.
The whole thing is 30.
Yes. So the smallest is 30 and the largest measurement is 44.9. Okay. So we have like 100 measurements in between 30 and 44.9. Okay. There is not a much variability here. Okay, the distance of the measurement from each other is not too big. It means it has less variability. Okay, now what about is it possible for us to find a number, okay, at the center, or which is the number which number will be at the center for this 100 measurement? Is it possible for us to find? So like from this observation, we can make that every numbers, they are close to what number? Can we pick one number? So can we say so we have 30 and 44, which is like 45. So if we take the middle number, that is 30, 40, it's like 37. So yeah, 30, we can just take 37 as the center number. Okay, so here every measurements they are centered about some numerical value. We will find that numerical value. Okay, and finding those numerical value means we are finding the mean, median, mode. Okay, so these numbers give us the central tendency. Now, the very first measure of central tendency is mean. So mean, it helps us to find a number. Okay, from the given data set we can find a mean, and mean is a single value, okay, that we can calculate from our data set. And what does mean give us? It gives us the average value, right? It gave us the average value of the measurement. And how do we find the mean? So we find the mean of a quantitative data set by summing all the measurements and dividing by the number of measurement contained in the data set. We add each measurement and we divide that sum by the total number of measurement. Okay, and we can write this formula in general. So we have x bar, okay, to represent mean. So if we are talking about the mean of a sample, okay, mean of a sample, we use x bar, mean of a sample. So x bar, and this mean of a sample, x bar, is equals to, so we have this notation. Have you seen this notation before? Yeah, so this is a summation notation. Okay, so x bar is summation of xi. So xi represent each measurement. Okay, and our I is running from 1 to, let's say we have n number of measurement, divided by n. N is the total number of measurement. Okay, for example, let's say we have x1, x2, x3, x4 up to xn. So this is our data set. Okay, so this is our data set, and we are trying to find the mean of this data set. Okay, so what we do, we add each of this data set, x1 plus x2 plus x3 plus x4 plus up to xn, and divide by the total number of measurement, which is n. Okay, and this is how we represent and this is how we write, okay, the summation of xi. Okay, xi is the measurement and our I is running from 1 to n, divided by total number of measurement, which is n. So this is the mean for the data set. Now, as I said, x bar is used for the mean of a sample. Okay, there is a notation for a population mean, which is mu. Okay, so this is our mu. So we use mu to represent mean of a population. Okay, we use x bar to represent mean of a sample. So if we want to find the mean age of this classroom, what will be the correct notation? Is it x bar or mu? So if we want to find the mean age of student of this classroom, do we use x bar or mu? No. Population is, this is the sample of students of ENMU. Okay, so we use the x bar. This is the sample. But if we are finding the mean of students, mean age of students at ENMU, which is our population, we use mu. Okay, so make sure to use the correct symbol. So x bar is for a sample. Sample is always small in size. Okay, population is always in large. Now, So our second goal of this course is making a generalization or making an estimate. The first is we try to gather information from the data set. Okay, we try to gather information, and second goal is we use the sample information to make a generalization or to make a estimation. Okay, now once we have a sample mean, okay, for example, if I have a sample mean age of this classroom, I can use that sample mean age of this sample to make an estimate of a mean age of these ENMU students. Okay, so we can use our X bar, which is the mean of a sample, as an estimator or approximator for the population mean. Okay, so this is making an inference, this is generalization. Okay, this is an estimation. So we can use mean to mean as an estimator for population mean. Okay, now we have this example. Let's find the mean for this example. Now what will be the correct notation? So we have to find the mean of these measurements. So it does tell us sample measurement, right? So we will be using X bar, not mu. Okay, so our X bar is equals to, how do we find mean? We add each measurement. So 5 plus 3 plus 8 plus 5 plus 6 and divide by total number of measurement. How many do we have? 1, 2, 3, 4, 5. So we have 5 measurement. 5 plus 3, 8, 8 plus 8, 16, plus 5, 21, plus 6, 27, divided by 5, and this is 5.4. Is it 5 point? Okay, 5.4. So 5.4 is the mean for this sample. Now, so if you are only given mean and you don't have this data set, can you imagine your 5 data set if the mean of that 5 data set is 5.4? So 5.4 is the mean for the 5 measurement, and we don't know that those 5 measurement. Okay, now with the help of this mean 5.4, can you imagine what could be the measurement, like possible measurement? You may not be accurate, you may not be able to find exactly, but you can expect, right? You can just find the possibilities. Do you think that will it be possible to have 50 as a measurement for this out of 5? Can we have a 50 out of 5 measurement? Mean is 5.4, and can we imagine that 50 will be there in that 5 measurement? Is it possible to have 50? No, right? Or yes?
If you have the rest of your numbers are really low.
Okay, how far you can go now? Okay, for example, if you take like out of 5, so if your one measurement is 50, so the remaining would be, it should be I think negative numbers, right? If we have a negative number, then I think yes. But since we have the data set, and it's always like a positive, right? So if we are now, so in this case, like from this mean, we can have an idea of those 5 measurement. Like it's going to be very close to 5.4, right? So we like 5.3 or like 6, 7. So we can describe our data set with the help of this mean. Okay, that's what we are doing here. So we are trying to find a number which is mean here, and using this mean to describe our data set. Okay, so this is one of the way to describe our data set, calculating or finding the mean. The next method or next example or next way to find the central tendency is finding the median. Okay, so here the median of a quantitative data set is the middle number. Okay, so median, it gives us the middle number when the measurements are arranged in the descending or ascending order. So in order to find the median, we have to arrange our measurement in the ascending or descending order. Okay, and once we have our measurements in the order, we pick the middle number. That middle number is the median. Okay, So if we are calculating the median of a sample, we use M, okay? And if we are calculating the median of a population, we use eta, okay? So this is eta. Mu is for population mean, okay? Eta is for population median. X bar is for sample mean. M is for sample median. Okay, now for the same data set, let's find the median. So we have 5, 3, 8, 5, 6. First step, we arrange our measurement in the ascending or descending order. Okay, so let me make an arrange in the ascending order. So this
Example at the bottom.
oh, do we have a same? Oh, okay. So let's do this example. Then we'll be back. So we have this measurement. We have 7 measurements, and we are asked to find the median of this sample. So let's start by arranging this measurement. So 2 is the smallest, then 5, oh not sorry 5, we have 4. So the next is 4, so this is gone, then we have 5, 5, so we have 2, 5, then 6, we have 7, we have 20. Okay, so you arrange your data set in ascending or descending order, and we look for the middle number. So we have 7 measurement. So which one is the middle? 5. So how many measurement do we have on the left of 5? So we have 3 measurement, and we have 3 measurement on the right of 5. So 5 is at the center. Okay, so this 5 is the median. 5 is the median. Okay, so if we have odd number of measurement, then the middle number is the median. Okay, sometime we might have n number of even number of measurement, and if that is the case, median is the middle of 2 numbers. So here I think if we how many part. Okay, so let's find that. So in part B, it tells us to eliminate the last measurement. So it tells us to eliminate 2 and calculate the median. So let's calculate the median here. So we are eliminating 2. So we are starting from 4, 5, then 5, 6, 7, 20. Okay, so we have even number of measurement. We have 6 number of measurement. Okay, so so we have 2 number in the middle. 5 and 6, these are in the middles, right? So we have 2 on the left, 2 on the right. Now if this is the case, so if we have even number of measurement, then the middle number, the average of these 2. Now what is the middle number for in between 5 and 6? 5.5, right? Which is the average of 5.5 and 6. So median is, you find the average of these 2 number, 5 plus 6 divided by 2. Sorry, this is 5.5. So 5.5 is the median. Okay, so here if it's odd, there is always 1 number at the middle. Okay, if it's even, you find the 2 number in at the middle. So you take the average of those 2 number, you will get the median. Okay, now so here, so so here we have this frequency, we have this histogram. Okay, and on the horizontal axis it is mean. Okay, and the vertical axis is frequency. Now here, so this diagram, it tells us what the median does to the data set, what it does to the data set. So finding the median means we are finding the middle number, right? We are finding that middle measurement. And what it does to the data set is that it divides the data set into exactly 2 equal half. Okay, like here. So 5 is our median. Okay, so this is our median. And this 5 median, it divides our measurement into 2 equal parts. See, on the left we have 3 measurement, on the right we have 3 measurement. Okay, in the similar way, so here 5.5 is the median. So 5.5 is somewhere in the middle. 5.5. On the left of 5.5, we have 3 measurement. On the right of 5.5, we have 3 measurement. Okay, so median always divide our data set into 2 equal part. Okay, so that's why we have 50% measurement on the right side, and we have 50% measurement on the so we have 50% on the left, and we have 50% on the right of the median. Now, is that what? Now, is it same for the mean? Does the mean divide our measurement into 2 equal part? Now, if we go back here, like for this data set, so 5.4. So if we arrange 3, 5, 5, then 6, 8. 5.4 is somewhere here, right? 5.4. See, on the left we have 3 measurement. On the right we have only 2. So median it divide exactly into 2 equal half. Okay, so whenever you have a median, you can think that you can always imagine the 50% measurement is on the left and 50% of the measurement is on the right. Okay, now for the same measurement, let's find the mean. Can you find the mean for this measurement and for part B as well? I want you to find mean for this sample. Make sure to use the correct notation. So we will be using, what is the notation we will use for the mean for this measurement? X bar. Okay, so we add all of these measurements. So 5 plus 7 plus 4 plus 5 plus 20 plus 6 plus 2 divided by, we have 7 measurement. Okay, that's 12, 16, 21, 41, 47, 49, 7. Okay, now in part B we are asked to eliminate 2. Okay, so let's eliminate 2 and find the mean. So we have x bar equals to 5 plus 7 plus 4 plus 5 plus 20 plus 6. So we are eliminating 2. Okay, divided by, we have 6 measurement, 6. 49, 47 divided by 6. 7.84. Okay, now, so instead of eliminating 2, what happens if we eliminate 20? And let's see, let's find the median and mean. Okay, now instead of eliminating 2, I want you to eliminate 20. So your data set is 5, 7, 4, 5, 6, 2. So we eliminated 20 instead of 2. So what will be the median and mean for this sample?
Mean would be
4.84. Okay, and median would be, so we arrange in the order, so 2, 4, 5, 5, 6, right? Okay, I forgot 7. So which one is the middle? This is gone, this is gone, this is gone. 5, right? Median is the 5. Now let's compare this median mean with this median mean. Now what difference do you find here?
just the mean is different.
So in both case, we had a same median 5, right? But the mean was, the mean for the first sample is 7 and for this one is 4.84. And what is the reason here? So this 20, so if you compare these numbers and 20, what can you say? So these numbers are very close to each other, right? 2, 4, 5, 5, 6, 7. They are very close to each other. Close to each other means they have less variability. Okay, but but the 20, it is very too far. Okay, so once we get rid of these extreme values, okay, our mean changes. Okay, but it does not affect median. Okay, so whenever we have the extreme values, having extreme values means having the very small measurement or a extremely large measurement. Okay, that changes the median. Okay, that changes our mean by a lot, but median it really is not affected by the extreme values. Okay, so here our median is 5. Okay, and this median is also one of the way to measure the central tendency. Okay, it tells, so it is a single numerical values, and we can use median to describe data set. Now once we know 5 is the median, how can you what would be your imagination for your data set? Okay, let me take a different, for example, your median for 7 measurement is 3. Okay, the median is 3. Now can you imagine 7 data set? The median is, the only given to you is median is 3, and you have to imagine that 7 measurements. Okay, so how are you gonna write here, like what will be your measurement? So we need to have a 7 measurement, but that 7 measurement must have a median equals to 3. So what is the very first thing when the median is 3 given to you? So it's in the middle, right? So we must have a equal measurement on the left of 3 means we must have a measurement, equal measurement which is less than 3 and greater than 3. Okay, we must have an equal number. Now, and we need a 7, right? So let's consider we have 3 here. So we need
1, 2,
3 more here, and 3 measurement here, and 3 measurement here, right? So 3 has to be less than 3. So what do you want to do? Like 1, okay, let's say 1, 2, 2, right? Or 4, 5, 6. Okay, so here our median, it also helps us to describe our data set. Okay, that's what we are trying to do, describing our data set with these single values. Okay, the next here is that now we call our data set to be skewed. Okay, so we call our data set to be skewed if one tail of distribution has more extreme observation. Okay, one tail means, so we have a data set, we arrange our data set in ascending or descending order. So let's take the right side and the left side as a tail. Okay, so and if we have the extreme observation means like extremely large or extremely small measurement, then we call it skewed. Like the one example we just had. Okay, this example. So let me rewrite that. So we had 2, 4, 5, 6, 7, and we had 20, right? Now if we look at this data set, don't you think this 20 is extreme observation? Like in comparison to this 6 measurement, 20 is extremely large, right? So it means this is a skewed data set. Okay, so whenever you have extremely small or extremely large, in a similar way, for example, let's say you have like -10, so it is extremely small in comparison to this 2, 4, 5, 6, 7. These numbers are extreme measurement, extreme observation. Okay, and in the data set, if you find extreme observation, then we call those data set as a skewed data set. Okay, now what about this example? Is it skewed? Do you think this is skewed? 5, 3, 8, 5, 6. They are pretty close to each other, right? So this is not skewed. Okay, so if we have extreme measurement, so if we have more extreme observation on the right, okay, it means on the right means like extremely large number. So if we have extremely large measurement, then we call it skewed to the right, okay? And if we have the data set with extremely small observation, okay, extreme observation on the left, we call it skewed to the left, okay? The histogram for skewed to the right, it looks like, so like in general, so we have measurements here and we extend, so we make a tail on the right side, okay? It means we have measurement on, we have extremely large measurement, okay? So if we have the tail, so having this tail on the right side means we have extremely large measurement, okay? So this is skewed to the right. And skewed to the left means we have a tail on the left side, okay? We have the tail on the left side, okay? It means we have extremely small measurement in the data set, okay? So having extremely small or large the measurement in a data set make the data set skewed, okay? If we have extremely large, we call it skewed to the right. If we have extremely small measurement, we call it skewed to the left. Now, is it skewed to the right or, okay, now let's forget about -10. Now, is this measurement or is this data set skewed to the right or skewed to the left? To the right, okay, because we have 20. Now, if you get rid of 20 and we had -10, and this data set would be skewed to the left, okay? If we have extremely small measurement, that is skewed to the left, and if we have extremely large measurement, it is skewed to the right. Okay, now if here, so if our data set is skewed to the right, median is less than mean, okay? So let's say, for example, our median is here, okay? And this median is always less than mean. So less than means is on the left side of mean, right? So if we have a skewed to the right data set, then median is always smaller than mean. If we have skewed to the left, then our mean is less than median. So our mean is on the left side and our median is on the right side, okay? So x bar is small than m if we have skewed to the left. The next, now if our mean and median is equal, sometime we might have a mean and median equals to each other, and we call that data set as a symmetric data set, okay? So we don't have any tail here, so we have mean and median at the same point, okay? So this point is a median and as well as mean. And if our mean and median is equals to each other, it is symmetric data set, okay? Okay, the last measure of central tendency is mode, okay? This one is easy. So mode it is the measurement that occurs most frequently in a data set. So whenever we are finding a mode, we are looking at a measurement that occurs more frequently, okay, which is the mode. Like here we have this example. Now in this example, which measurement occurs most here? Okay, so 1, 2, 3 times, right? So 9 occurs 3 times, so our mode is 9, okay? So in our previous data set, so for this one, what will be the mode? So which one occurs most? 5 occurs 2 times, right? So 5 is the mode. So if you have a data set with a mode 15, what does it mean for you? So in that data set, 15 occurs most, right? It occurs more frequently.
What's the symbol for the mode?
Mode or MO. So you can use MO or just write mode itself, okay? Okay, I think let's do this much for today. So we are done with section 2.3. If you have any question, let me know. I'll be here for a few more minutes. If not, I will see you next week.